And it's my great pleasure to introduce today's speaker, Professor Chris Cappa. So I've known Chris for 19 years. We started grad school in the same group. And so it's really fun to have him here to do a lot on the physical chemistry of water. And he did many elegant experiments, some of which were very simple, involving round jugs, some of which were very sophisticated, involving liquid microdepth. In his postdoctoral time at NOAA CSD, he worked a lot on the physicochemical properties of organic acids and other organic mixtures, understanding how they might contribute to condensable organic material. And since then, he's worked a lot on different aspects of carbonaceous aerosol and to a great extent on their optical and optical properties and their hygroscopicity. So today he's going to talk to us about some of what he's learned over the last many years related to optical properties of aerosol. So welcome, Chris.
So yeah, it's my pleasure to be here to talk with all of you. And I just want to say I'm going to be in town for 6 weeks or so. So I'd love to talk to anybody about this in the future as well. So I'm going to focus today on some work that I've done actually with Chris Limmer in this room on the properties of brown and black carbon as produced from biomass fires. And so just start here with this nice waffle here showing us the different shades that we can get from black to brown. And that's what I'm going to be really talking about today, is the different colors of particles and how those can evolve under chemical oxidation. Maybe this will change or not. Okay. So we can think about sources of particles to the atmosphere, and there's a lot of them, but one of the major sources of particles to the atmosphere is fires. Right, and so here's an example from just up the road from where I live in California. This is a big Northern California fire last year, and this is a big Southern California fire last year. Right, and fires are periodic, but when they occur, they release massive amounts of material to the atmosphere. And the majority of what they emit to the atmosphere, not counting gases, they emit a lot of gases as well, which will come to play later in my talk. But they emit a lot of what I'll refer to as black carbon and what I'll refer to as organic aerosol. And here's looking at a global budget of primary emissions that was put together by Tammy Bond here, looking at the black carbon budget. And you can see that open biomass combustion here is about 40%. If we add in biofuel combustion as well, we're well over 50% of global emissions of black carbon coming from kind of biomass combustion overall. And then if we look at organic aerosol, suddenly we're pushing up towards 90% plus. Again, these are very periodic events, but because we release so much material to the atmosphere when they occur, right, they are huge global sources of these materials overall. And what I'm interested in really is what are the properties of these particles that are emitted? And in particular, how can we relate the chemical properties of the particles to how they absorb and scatter light in the atmosphere. And so the reason that we might care about this, or one of the reasons that we might care about this in particular, is that absorption by particles has a large effect on climate, and in particular, it has a net warming effect on climate, right? Overall, particles have a cooling effect on climate, but the absorbing components of those particles can actually warm and can counter those effects to varying extents. And we might refer to this as positive radiative forcing, and there's actually estimates that put absorption by black carbon, and if we include brown carbon even more, is second only to CO2 in terms of the warming potential on the planet. But it's highly uncertain compared to, say, the absorbing by CO2 overall. There's large uncertainties both with respect to how black carbon behaves in the atmosphere and how much light it absorbs, but then also how much light organic aerosol absorbs in the atmosphere overall. And here's an estimate from the IPCC report from 2013, and you can see again these large error bars over here. Some of that's related to the emissions and quantifying the emissions, but some of that, in fact a large fraction of it, is related to understanding the properties and what happens when we process particles in the atmosphere. And I'm interested in trying to reduce those uncertainties really through process level studies to get at the behavior of these particles and their relationship with composition. So when I talk about black carbon and organic aerosol, or what I'm going to refer to generally as brown carbon, I'm talking about really two different things here. And so black carbon, if we think about the properties of black carbon, what it is ultimately, it really is the black stuff that you see, say, coming out of a diesel truck, right? But it also is emitted from biomass combustion. Characteristically, it's very strongly absorbing. So per amount that you have, right, per mass that you have, it absorbs very strongly, right? So I'm going to characterize that here with what I'll call the absorption coefficient. So that's the cross section per mass of material that you have. And we see that black carbon is pretty strongly absorbing, and it absorbs relatively flat over the entire solar spectrum. Right? So it absorbs light across the entire solar spectrum. It tends to be refractory, meaning it's not really sensitive to heating. It doesn't degrade very well. It doesn't really chemically change too much overall, and it's nearly entirely from combustion, right? It's not produced in the atmosphere through any chemical reactions, right? It is produced from combustion overall. Now we can contrast that with what I'll call brown carbon here. Brown carbon is really absorbing organic aerosol media. And we can think of brown carbon as having a few key characteristics. One, it has comparably weak absorption. If we compare it to black carbon, I'm just illustrating that here with kind of this cartoon of how it might compare here, right? And we just see it's much lower, right? Per mass of material that you have, it absorbs much more weakly. It's a comparably weak absorption. It is also, rather than kind of one thing, when we think of like black carbon, it's much more like one thing. When we think of brown carbon or organic aerosol, it's lots of things. Right? There's lots of individual compounds that make up organic aerosol, and each one of those compounds has its own unique properties, right? And those can transform as well when the particles are chemically altered, and they can interact in different ways to dictate how much a given particle is going to absorb, right? That ensemble of molecules that you have. But that also means that really much more than black carbon or brown carbon can have very variable properties, because it depends on the mix of chemicals that you have making up your brown carbon overall. One thing that characterizes brown carbon is that the absorption tends to be fairly weak at longer wavelengths, but that absorption goes up pretty steeply as you move towards shorter wavelengths. And I'm not really getting into the UV here, but you can potentially have a notable impact on the UV budget, potentially on things like ozone production within urban regions if you have a lot of brown carbon around. I'm generally interested in the behavior more out in kind of mid-visible region where you're going to have a bigger impact on climate overall. And then one last thing about brown carbon here that distinguishes it from black carbon, some of it is emitted, and a lot of it's emitted from fires, right? It's emitted from combustion directly as primary particles, but it can also be formed in the atmosphere from chemical reactions or transformed in the atmosphere from chemical reactions made. You can either produce it or you can degrade it, right? It can be chemically transformed. It depends on what we have. And I'm really interested in what those transformations are and how they affect the properties of brown carbon that we have. Now, one thing to note here, right? Black carbon does absorb much more strongly than brown carbon. So we might say, who cares about brown carbon? Let's focus on black carbon. Well, if we look at the amount of stuff that we emit to the atmosphere, though, so here's the ratio that we might see between organic aerosol and black carbon that we see from primary biomass combustion. And so these are measurements. These are actually the measurements that I'll be talking about today. We see a wide range of ratios, right? This is just primary material, but kind of our median value here is about 10, right? So we have not on average, but in the median, right, 10 times as much OA as black carbon. So even if your absorption per mass is 10 times smaller, right, the total absorption can be equal, right? So that's why we care, right? There's a lot more OA than there is BC usually, or at least in the median and on average, but the brown carbon tends to be more weakly absorbing. In a sense, that's a good thing. If brown carbon was absorbing with black carbon, we'd have a much bigger issue to deal with in terms of the warming of climate by particles overall. So we can think about then, where is understanding lacking when it comes to both brown and black carbon? And I'm going to try to touch on all three of these aspects here today. So the first is thinking about, the variability in brown carbon overall. What drives the variability in absorption by brown carbon? Right? How does that link to the composition of those particles overall, and how does that link to things like what's combusted, what's being burned, how it's being burned overall? Another really important question is how is brown carbon absorptivity, especially brown carbon from biomass burning, altered as it ages in the atmosphere, right? Both the properties of the primary stuff that's emitted, as well as the gases that are oxidized, potentially forming new material, right? How does that overall ensemble change, and how does that change the overall absorption by the particles that we get from biomass combustion? There's actually not there's not enough known about that for sure. We're learning more and more, but we haven't had enough investigations really of the mix of what you get when you mix the primary particles with the gases and think about what happens to that overall ensemble here. And I'm showing here on the left one example of some ambient observations here. These are from Forrester et al., where what they observed is that over about a day time scale, that the absorptivity of brown carbon went down dramatically. It went down dramatically. This is looking at how the absorptivity is going down over about a day time scale. That's one study. They also have another study from the same group where they looked at higher up in the atmosphere, and they see no change with time in the atmosphere. Right, so we're interested in what drives that variability in behavior in different environments. And the last thing that I want to address, I'm going to focus on brown carbon a lot, but there's also some questions associated with the absorption by black carbon here. And the key thing that determines the absorption by black carbon is, one, how big is that particle? How much mass do you have? Right? That's going to determine the magnitude of the absorption, but also the absorption by black carbon can be influenced when it mixes with other stuff. If you condense material on top of black carbon, right, that can actually lead to an effect where the absorption by that particle goes up, even if you condense stuff that doesn't absorb on that particle. Right? It can actually lead to an increase, at least theoretically. You can do it in lab, but there's a lot of questions about how much that occurs in the actual atmosphere or for complex systems. The results are all over the place. Right? And I'm illustrating that here with some work that I did a little bit ago, where we say, here's our lab experiments here going up, where what we're looking at is how much absorption you get by your black carbon as a function of how much stuff you coat on that black carbon. Right? You can see that it's going up here. And here's what we saw when we looked in the field. Right? So we see these differences, and we're trying to understand these differences overall for complex systems here. So I'm going to try to address all these questions today, at least to some extent, in the context of thinking about biomass combustion emissions here. So for today, the overarching question that I'm going to try to deal with is really, how does photochemical aging modify the properties of particles in biomass smoke, starting from what they come out as to what they transform to. And I'm going to talk about the FireX study. That's where we did our experiments here overall. We'll look quite a bit here to set the stage at the properties of those primary particles. We'll dive into the influence of photochemical aging overall, and I'll try to explain our observations a bit through a chemical model and thinking about the chemical processing that goes on. So let's get into it. So our experiments here that we did were during the FireX study. I don't remember what FireX stands for. It's an acronym. This was a big study at the Missoula Fire Lab, okay, and it involved a whole bunch of people who came out. You can see this is just some of the instruments here in this room. Our stuff is right here that we ran. And the basic framework for this study is that next to this lab here, there was this big burn chamber. Okay? And we have this big shaft here where we set different fuels, flame down here, and the smoke is conducted up that shaft where we sample it down then to the various instrumentation as fast as we can, trying to carry the particles and the gases to this other room where we can distribute it to all of these instruments overall. And in our case, we're going to take this and we're going to actually sample that smoke, the particles and gases, into a small reaction chamber here overall. And what we're interested in is characterizing both the fresh emissions, what comes out directly, and then what happens when we age those. And just to give an illustration of the variety of things that we burned, right? We burned things from ponderosa pine, all the way to rice straw, all the way to rotten logs in the end. A wide range of different fuel types, many of these of particular relevance to the Western US. That was one of the themes of this overall study, but also things from far away. For example, we had Indonesian and Alaskan peat, and we had, that's about as far away as we got, but a wide variety of fuels here in the end. And the key here is that each of these fuels burns differently, right? It has a different composition, it emits different things. And the question is, how does that translate to variability in the properties? Okay. So we sample the smoke, and what we're interested in doing is photochemically aging, right? So we take our fuel, we combust it, we sample it into our chamber here. We got our mini chamber, we called it, and we sample our particles and gases in. And what we have is some UV lights on the side. We add some ozone. There's some water vapor in there. We turn those lights on, and that initiates some photochemistry, creates OH radicals, right? And then we can oxidize the smoke and the gases with these OH radicals. And then we sample those particles and the oxidized gases as they're aging into a variety of different instrumentation here to characterize the changes over time. And through this process, we did 50 distinct experiments. That's different burns, different fuels, right? And we're going to look at the variability across all of these. And I should say, this is a collaboration with Jesse Kroll's group at MIT, and Chris Lim played a major part in these experiments overall. All right. So a typical experiment works like this, and I'll illustrate some of the things that we saw, which is kind of single experiments, and then what we'll often do is look at the ensemble results overall. So here's a typical experiment for subalpine fir. So what we do is first we start burning our subalpine fir, sample the smoke, start filling our chamber. We start with, well, kind of nothing in it. That's off the graph here. So we have a totally empty chamber, well, that's air, but totally clean of particles and gases. And we sample in. We let the burn kind of finish. We stop sampling. We let it equilibrate for a little bit. We stop sampling. We start sending in clean air to flush through, and we start sampling for a while here, just our particles that we have in our chamber. So first we characterize the particles as they came out, after a little bit of dilution as we sample them into the chamber, right, which is a process that happens in the atmosphere. It's aged downwind of a fire. But so we get our primary particle. And then at some point we turn on the lights, right? We turn on these lights, we start to induce photochemical aging overall. And signals overall tend to keep going down. Okay, so overall we see a downward trend. That's just because we're diluting things over time, right? That's all that's going on there, is we're diluting things. But some things go down faster than others, and that's an indication of something happening, right? In this case, I can tell you this is an indication of formation of organic aerosol from the chemical oxidation of the gases in there, right? And so we're going to see things like this overall, and we're going to think about how the particle composition evolves, how the optical properties of these particles evolve over time in a variety of different ways. And so we characterize these with a whole bunch of different instruments. So I'll throw a bunch of acronyms at you just to give you a sense of what we measured. So in terms of particle composition, we characterize the kind of bulk composition of the particles using an aerosol mass spectrometer. That gets us the total non-refractory particulate matter. So that's the organic aerosol components and then the inorganic components of those particles overall. So that's kind of the bulk average behavior. We also separately had a slit particle aerosol mass spectrometer, which is similar. It characterizes mostly the non-refractory components, but also adds in measurement of black carbon. So that adds this element of measuring black carbon. And further, this actually only measures these non-refractory components when they're mixed with black carbon, right? So it doesn't, if something doesn't have black carbon in it, we don't see it with this experiment. So this tells us about just the stuff that's mixed with black carbon. This tells us about everything. Okay? Then we also characterize the black carbon itself using a separate instrument over here in terms of the concentration inside of a single particle slit photometer. We characterize the optical properties using a combination of photoacoustic spectroscopy and a cavity ring down spectrometer. And so we measured light absorption, right? How much light the particle absorbed at a couple different wavelengths that span the visible range from 405 nanometers. So that's kind of down at the close to the UV, right? Kind of reaching the UV, 532 nanometers, and then far out into the red at 781 nanometers. I'm going to primarily focus on the 405 nanometer measurements today. Keep this into the blue, but the results translate to the other wavelengths as well. And we measured extinction also as well at 405 and 532. And then finally, we measured the composition of the gases in our chamber here using a proton transfer reaction mass spectrometry, or H3O plus SIMS, and then also an iodide SIMS overall. And this gives us an ability to characterize both the initially emitted compounds, kind of the less oxidized compounds, as well as the heavily oxidized compounds that are formed from the oxidation. And today, I'm really only going to take advantage of this H3O plus SIMS measurements here. Okay. So let's start with primary particles overall. What did we see of what came out? So the first thing that I'll note here is that, and this should surprise nobody who's ever thought about biomass burning, our particles are mostly organic aerosol and black carbon. Right? That's what we see. There's very little other stuff in there. There's a small amount of sulfate and a small amount of chloride that we see. Mostly organic aerosol and black carbon. The other thing that we see is that this organic aerosol to black carbon ratio varies dramatically between burns. Up there, that's the total average over the entire campaign. But if we look at individual burns, we see a huge range in these organic aerosol to black carbon ratios, anywhere from less than 1, where you're black carbon dominated, all the way up to 10,000, right, where you're completely organic aerosol dominated. So there's huge dynamic range there. And what we find is that a lot of properties tend to vary continuously with this ratio. It's a really good predictor of a lot of different optical properties and also a few chemical properties overall. And so I'm illustrating that here, looking at the single scatter albedo that we characterize. So the single scatter albedo is just how what fraction of the total extinction comes from scattering. So 1 minus this tells you about how absorbing the particles are. And so these are very black carbon rich, and so they absorb most of the light that's incident on them. And these are very OA rich, and we see that those tend to absorb only a small fraction of the light that's incident on them overall. Other things that tend to vary continuously with this parameter here is the absorption angstrom exponent. We'll look at that in a minute, but that characterizes the wavelength dependence of absorption, right? Larger values mean that your absorption goes down faster with wavelength. Smaller values means that it goes down slower with wavelength. So it tells you about how that absorption carries out over the entire solar spectrum. You can also think about the volatility of the OA that we have. And when we heat the particles up, so we occasionally heat the particles to see how much stuff would evaporate. And what we find is that the volatility of these particles over here, these ones like to evaporate a lot more easily than these ones do, the organic component of them as well, right? And also, as we'll see, the black carbon coating amount actually depends on this a lot. So this huge range and a lot of relationships of different properties between things. Now, in the end, we have this huge range, and so one of the things that I'm going to do for the rest of the talk here is kind of classify these particles into different categories here, right? And that's because we see that the properties vary somewhat continuously on this axis here. So I'm just going to group things according to different properties here, right? So I'm going to talk about the things that are very BC rich. So these are going to be one class of particles here, and I'll try to use this color scheme consistently here. So these dark blue ones are BC rich, and then the dark red ones are the really OA rich ones, and then we'll have everything in between. Okay, so I'm going to try to use this. We could ask, what are these things? And if we start to classify these, why do we get this wide range? Well, it really comes down to, if we look over here, These are the things that when you take a match to it, right, they really go up in flames, right? You see the fire, you see the flames going on very, very readily. So we get things that light on fire, including building materials, some wood of that sort. One of the people on this study really wanted us to take like a bunch of plastics and everything else that you might get in a house and throw it in there, but he got shut down on that one. In the end, so this was just wood from building materials overall. But then over here, what we see is the things like the rotten log, the peat, the dung, the things that don't actually burn very well. And when you try to set them on fire, they don't really flame. They just kind of smoke at you overall. And that's what largely drives this huge range. And then kind of everything in between is combinations of all those in different ways. Okay, so let's look a little bit more at some of these properties that these particles have. So here's two in particular that become important for the optical properties besides single scatter albedo. On the left here is the total absorption by the particles divided by just the black carbon concentration, right? So we can think of this as if we pretend that the organic aerosol is not absorbing for a minute, right? And we attribute everything to black carbon. This would tell us how absorbing it is, right? And what we see is that this value goes up pretty readily. This is at 405 nanometers. You see something similar at all the other wavelengths, and we'll look at that in a minute, but it goes up pretty dramatically here. It goes up much more dramatically than we would ever expect if we didn't have brown carbon. This is a pretty clear indication of brown carbon here overall. If we couple that with the observation that this wavelength dependence of absorption, this angstrom absorption exponent, goes up strongly with wavelength, this is again a really clear indication that we have brown carbon, because black carbon has a generally weak wavelength dependence. You might remember down here, back to 1, and we're heading right towards 1, right? Whereas brown carbon has a much steeper wavelength dependence. We're heading up that way. We're moving really just from a black carbon dominated system to a brown carbon dominated system here overall, right? Something that I find really interesting about this as well, that was looking at optical properties. If we look at where the material is in these particles, right? I told you we had one instrument that measures just the stuff that's mixed with black carbon and one that measures everything, right? And if we look at the fraction of the organic aerosol that's mixed with black carbon relative to the total, what we find is that when we have these really flaming particles, these BC-rich particles, most of the organic aerosol is mixed with that black carbon. But as we move over here to these very organic aerosol-rich particles, now we can think of it as only a handful of those particles have black carbon, right? Most of them actually don't have black carbon over here, right? So we see that the mixing state is evolving depending on what we're combusting as well and how we're combusting it. Related, if you look at how much organic aerosol there is in those black carbon containing particles in the end, so the organic aerosol to black carbon ratio for just those particles, in the end we see that it's going up here as you have more and more OA-rich particles again. So when you have a lot of OA relative to BC, you have very few particles that have BC, but those that do have black carbon have a lot of stuff mixed with them, right? And those down here, where most of the particles have black carbon, but when they do, they don't have that much OA in the end. So there's this interplay in the mixing state and how you combust things here overall. That ultimately impacts the optical properties of these particles overall. So one thing I mentioned here is this concept that black carbon, right, when you coat stuff on it, you can increase the absorption, even if you don't have any absorption by that coating material. Now, a classic way to think about that is to look at the behavior of the particles as a function of wavelength. Because when you go out to longer and longer and longer wavelengths, you expect brown carbon to contribute less and less and less. So you can look at long wavelengths and start to assess just the properties of the black carbon, or at least largely the properties of the black carbon. And so if we look at this parameter here again, the mass absorption coefficient normalized to black carbon, right? And if I look at that for our longest wavelength measurements over here at 781 nanometers, if I look at that as a function of how much stuff is condensed on the black carbon, and so how much coating material I have on the black carbon, that's what's down here, is the ratio between coating material to black carbon. What I see is that there's almost no dependence here. It's a pretty flat line. That is absolutely what you would not expect if stuff was condensing on the particles and causing an increase in absorption, right? This is actually fairly surprising. I was not, well, I was kind of expecting this, but I'm still surprised by it. But we can actually explain this, and it largely has to do with just how that material that we have, because this is an ensemble measurement, how is that material distributed across the total number of particles that you have? This is just really an indication that you have some particles again that have a lot of stuff coated on them, some that have very little in the end. So it depends on that distribution overall. If we look at these other wavelengths, right, these shorter wavelengths where we might think that brown carbon is going to have a bigger and bigger influence, we're going to shorter and shorter wavelengths, suddenly we start to see some dependence here, right? Things going up here. That's simply because we're adding more brown carbon, right? Because now we have more and more other stuff compared to black carbon here going up overall. This is really a clear indication, again, this difference as a function of wavelength is a really clear indication that brown carbon is really driving the show here for these primary biomass particles. And we can see that even more clearly if we look at the same parameter here, this mass absorptivity relative to black carbon as a function of the total OA to black carbon ratio here. So not just the stuff that's mixed with black carbon, but kind of everything that we have. And suddenly we get these really nice smooth curves here where basically what we're looking at is a mixing between brown carbon and black carbon in variable amounts. Right? This is exactly the shape that you would get if you just mix those overall. And so this is really just showing that, again, brown carbon is driving the show. Even out at this longer wavelength, there's a little bit of brown carbon absorption. Okay. So let's turn to that brown carbon. And so if we think that brown carbon is driving the show, we can actually derive the optical properties of just the brown carbon just by taking a difference between our observations and what we would expect for black carbon, for pure black carbon. And I should mention we can get our values for pure black carbon just by extrapolating this curve, right? So we can get that from our experiments, so we can do this in an internally consistent way. And so when we do that, if we look at just then the mass absorption coefficient for just the brown carbon, so that's the absorption by the brown carbon divided by the organic aerosol concentration now here on the left, what we find is that that parameter too depends on the organic aerosol to black carbon ratio. And this is actually similar to what Rawad Saleh saw a few years ago for similar measurements, although we managed to extend this over a much wider range and narrow the error bars quite a bit. So we see this strong dependence where the stuff that comes out when you have very black carbon rich particles is more absorbing per mass than the stuff over here. Suggests that there's a chemical variation going on overall. And that's implied here also by the angstrom exponent of just that brown carbon, right? We know that the angstrom exponent went up for the total particles, but if we just look at that brown carbon, we also see that it's also having a longer wavelength dependence up here. Again, that's suggesting some chemical change in the particles as we vary, say, this parameter overall. And then we can think about what this means in terms of what's doing what, right? Is the black carbon winning? Is the brown carbon winning for these different conditions? And so we can talk about the fraction of absorption by brown carbon. This is at 405 nanometers. And we see it varies from anywhere from very little, right? It's a small contributor, to it's the entire show over here, right? So we could say sometimes brown carbon, we could almost ignore it, right? Other times we ignore it or peril in terms of kind of understanding the overall behavior. Okay. So I've been mentioning, right, this could be driven by chemical differences, right? That's what's implied by these observations. So one thing that we looked at is there's a lot of things that don't seem to correlate. There's a lot of things that don't seem to correlate. But there are a few things that at least have reasonable correlations in the end. And one of those is if we look at the brown carbon absorptivity, so same y-axis as this graph here, and we compare it to what we derived for the nitrated organic fraction of the OA from the aerosol mass spectrometer measurements here, right, we see that there's a general increase in the absorptivity as the nitrated organic content of the particles goes up, suggesting at least that having nitrated organics is an important aspect of getting absorption in these particles, or at least correlates with the total absorption overall, right? So a chemical change. And this is consistent with some observations from Alex Laskin's group over here, where they see that things like nitroaromatics here, which is blue traces just for one burn, do make up a substantial fraction of the total absorption that they see at different wavelengths. Although I'll note, they're not, these nitroaromatics in this case are not the only thing. There's a whole variety of other things that absorb. So it could just be that this is a predictor, but it's not the only thing that's changing, right? So the question though is, what happens when we turn on the lights, right? That's a lot about the primary part, but what happens when we turn on the lights? Lots, right? Lots happens when we turn on the lights. So here's an illustration for one experiment, right? And so first, let's start on the left here, right? We can determine how much we've aged the particles here by looking at, for example, the change in the dilution corrected signal for deuterated butanol, right? So deuterated butanol doesn't exist naturally in the atmosphere, so we can monitor it uniquely in our mass spectrometer, and we can figure out how much of it goes away to figure out how much OH we've had in our chamber. And so we can use that to figure out an equivalent aging time, and so I'm going to be reporting aging times here, usually in days. Okay, so this is days of kind of equivalent aging based on how much OH we've exposed the particles to. And this is one example for a ponderosa pine experiment. We turn the lights on at 0, and we suddenly see that the organic carbon ratio for the organic aerosol, or sorry, the oxygen to carbon ratio for the organic aerosol shoots up, right? Shoots up quite fast. And if we look at in this experiment here, the organic aerosol to black carbon ratio, it also shoots up very fast, right? In day timescales. We're seeing rapid changes in our system when we turn on the lights. This is for one example. We can look at this for every experiment though, and this is an example from a paper that Chris published earlier this year, and we can look at how much OA mass, how much new organic aerosol mass we make relative to the primary particles as a function of aging time. You see huge range of values, right? How much we make varies a lot between experiments, depending on how much we age them. That's one thing that we see. You see, the O to C's are always going up, H to C's are always going down. This marker that people like to use for biomass burning quite often, F, the fraction of the mass spectrum that is due to the C2H4O2 ion. It's a kind of characteristic ion of biomass burning. It goes shooting down here, disappears down to this background. Right, so massive, fast changes going on. And one of the really neat things that Chris showed is that this variability in that top left graph, right? That variability in how much OA mass you add is very simply related to how much stuff you started with in the chamber, right? If you have more stuff to oxidize and turn into new material, you can make more material. It's as simple as that, right? There's some nuances to that in terms of thinking about exactly which molecules are driving that. But our conclusion overall in this is that it didn't really matter if you looked at one molecule, two molecules, or all the molecules. In fact, all the molecules was a pretty good predictor. Even a lot of those that we don't think form new organic aerosol material. It worked as a pretty good predictor, just the total mass that we have. But overall, we see that we're making new mass overall. So that's for some chemical changes. If we look at the optical properties, we also see substantial changes with aging. Illustrated here on the left for the same ponderosa pine experiment. Here's this mass absorption relative to black carbon, just goes shooting up here, right? The particles become much more absorbing per unit black carbon mass. The Angstrom exponent changes quite rapidly as well. And one of the things that we noticed in this case is that the mass absorption coefficient for just the brown carbon, again obtained through difference, actually shows some relationship with the O to C ratio, right? As we're aging these particles overall. So that's one experiment. Again, we're going to look at the average behavior now for each class. Remember, I classify these into these different categories based on whether it's very OA rich or very BC rich to try to simplify the behavior. And so we look at first our BC rich particles here. So these are the dark blue, those are the BC rich ones. We look at that average behavior overall. We see really big and rapid changes in terms of how much OA we have relative to black carbon. We make a lot of new stuff is basically what that's saying. If we look instead at the stuff that starts very, very OA rich when we turn on the lights, we actually see a lot less of an increase overall, because there seems to be a lot less gas there to oxidize and form new stuff. And then we see everything in between. And in fact, how much new mass you seem to add scales a bit with kind of where you start on that curve of more BC rich or more OA rich overall. Okay? So that's looking at kind of the amount of new stuff that we form in our chamber. But we can then think about that in terms of what does that do to the optical properties. Over here, we look at the mass absorption coefficient normalized to black carbon. Again, each one shooting up on these average different classes. Larger changes in general for these BC rich ones, smaller changes in general for the OA rich ones here overall. In general, things going up overall, although perhaps for these really OA rich ones, maybe coming down overall. And these step changes are just not every experiment went for the same amount of time and fewer number of averages or fewer number of experiments after some of those times. And then we can look at the overall angstrom exponent again. Again, big changes here for our very BC-rich particles. There's smaller changes as we go to more and more OA-rich, and perhaps even coming down here. But one of the things that I tend to note over here is what seems to be an evolution towards a very similar end state overall. We can look also at the brown carbon itself. So over here is the mass absorption coefficient for just brown carbon. We see that overall, everything comes down over here. Although there are these interesting increases right here at very early times for these less absorbing starting points. Right? These are the more OA-rich systems here and the more BC-rich systems here. You see these initial increases here overall. For the angstrom exponents, again, things are going up here, things are going down here, but actually converging to a similar state. It's actually suggesting over time that all of our systems here in terms of brown carbon properties are evolving towards a similar state. Okay. So we can think about why. What can describe all of these changes here overall, right? And I think we can actually describe it pretty simply. I'm going to briefly describe the chemical model that we're using to characterize this as an empirical model. In the end, the way that we're going to apply it. But here's the basic concept. We have three different processes that can be going on. One is we make new material, we make secondary organic aerosol, it condenses, right? It has a different color than the primary stuff, so the ensemble average changes. Pretty simple. So we make some new stuff that has different properties. Another thing that can happen is that we can heterogeneously oxidize those primary particles and the secondary material overall. Of course, these are going to be going on at the same time. And the third thing that could be happening is that photons could actually come in and photo bleach the particles or change their properties overall directly through photons. For our experiments, probably this is too slow. In general, our photon flux wasn't high enough for this to really matter on the time scales that we have. So I'm going to focus on these upper two. And so what we're going to try to do is we're actually going to try to simulate a number of the different changes that we observed here in terms of that absorptivity of the brown carbon, right? That OA to black carbon ratio, and the oxygen to carbon ratio, and a few other things. We'll introduce all these different processes plus a couple specific things for our experiments, dilution, for example, particle losses to walls. So we're going to include these additional physical processes. Then we're going to include a couple constraints here, right? We're going to include a couple constraints. One is going to be, we're going to try to use class-specific primary particle properties because we know that they varied. And we're going to use our observed VOC identities to try to get a handle on what the properties of the oxidizing gases should look like. And so in the end, after staring at all the gases that we had, and they measured over 100 different individual gases, and I didn't want to simulate 100 individual gases, I concluded I could do it with three. Okay, three gases. One is those that react fast, those that react a bit slower, and those that react very slow. So this is like a fraction of a day time scale. This is like a day time scale, and this is like a multi-day time scale in terms of their rate coefficients with OH in the end. And then we're also going to add in that when you do this, you make some stuff that can just form SOA, We're not going to worry about the details of partitioning. We're just going to say you make SOA. And then there's a bunch of stuff that doesn't make SOA, just hangs out in the gas phase. And that stuff can get oxidized again, and some fraction of that will make SOA now. So you can get kind of this continuous aging overall. And so this is our very simplified chemical scheme. I'll justify this very quickly by saying, here's all the things that we measured, right? They have a distribution of OH reaction rate coefficients over here. And if you squint at this enough and stare at it and look at all these individual things, and you break it up, these are about the equal numbers of things here overall in terms of the fast reacting things, the slow reacting things, and the very slow reacting things here overall. Okay? And it turns out that these fast reacting things tend to have more aromatic content than the slow reacting things and the very slow. This is dominated by benzene here. This has a lot of monoterpenes as well up here, but otherwise there's a lot of aromatic content. There's also a lot of furans up there. But we're going to group these and kind of use these general characterizations in terms of about how much we have of these as well. Okay? And what we find when we take this model, and we're going to tune it, right? I don't know all the properties a priori, so we're going to allow for some tuning. And what we find is a couple things. At first, the first generation SOA, the stuff that forms either from fast, slow, or very slow, drives the initial changes. And the fast SOA is really responsible for these fast changes at first, and you get the slow, and you get the very slow, right? And these have to have approximately this proportion to make sense, to explain our observations on balance. You have mostly slow stuff and a bit of fast stuff. And a little bit of very slow stuff. The other thing that we find is that the second generation, right, allowing those gas phase products to keep reacting is really key to this continued evolution over here. If you don't allow for second generation stuff, then stuff basically just goes flat and you're done. Okay? The last thing that we find is that heterogeneous oxidation becomes especially important at these longer times here. Right? At shorter times, it's not fast enough with the assumptions that I've made to drive anything, but at longer times, it can become really important. So this is looking at how much stuff we form, but I'm really interested in the optical properties. And what we also find is that the different SOA types that we form have different properties. Okay? So what we find is that this fast-forming SOA, the stuff that reacts fast, and the stuff that has the highest aromatic content, and where incidentally we had a lot of NOx available in NO form, tends to form particularly absorbing particles, fairly absorbing things. And that's actually what explains this initial increase here. At least that's how we can explain these initial increases here. And it becomes more apparent when you have more weakly absorbing stuff because this is more absorbing than this, so it goes up, right? But compared to this, it's less absorbing, so it goes down. It's a mixing question. But then you start to blend in less absorbing stuff over time, and that's what drives this continued downward evolution. And then you have heterogeneous oxidation continuing you down here overall. And these are all tuned parameters. These were determined by fitting to these experiments to give a general sense here overall. Right, so we see a wide range of properties of the SOA that we can make overall. So we evolve from fairly absorbing stuff to more absorbing or less absorbing to even less absorbing over time. But the time scales are actually pretty long. They're not 1 day. Well, they're 1 day for formation of absorbing stuff, but they're longer than that we observe at least for these decay timescales. Okay. So overall absorptivity is going down, but I want to make one more point here, which is that although the absorptivity is going down, right, the amount of absorptions per mass of stuff that we have is going down for the brown carbon, we're also making stuff, right? That's what's driving this decrease, is just a dilution effect, right? We're making new SOA. So the overall absorption, dilution corrected, is actually going up. Right? It's actually going up because the stuff that we're making is absorbing. And so we can think about that here in terms of the absolute ground carbon absorption. So this would be if I take the total OA that I have, right, relative, and use those time-dependent mass absorption coefficients, which are going down, right? It goes up a lot for these. It goes up less for these overall, just because of the mix of materials that I have. If I look at these brown carbon fractions of absorption, over here, it actually has a very limited effect. but there's a range where you actually have a very big effect, and that's because you're basically making browner stuff in that case compared to the primary material. So just because stuff is getting, let's say, less brown overall, less absorbing, doesn't mean that the total absorption is going down in the end. Okay. And that's all I had, right? So really a couple of key points, right? Primary biomass burning particles have a wide range of properties, right? Photooxidation, we find it leads to a large production of new mass, of new secondary aerosol mass. That's proportional to how much VOC material you start with. These VOCs, when they oxidize, they contribute on this kind of continuum of time scales. And then overall, the SOA that is produced from oxidation is somewhat absorbing. It's, in some cases, quite absorbing, in some cases, less absorbing. And understanding kind of that continuum of oxidation time scales and of what you're forming is going to govern how these plumes of biomass burning evolve in the atmosphere. And I just want to finish by thanking everybody who helped with this work. And again, I'm going to give Chris a big shout out because he was there the entire time making measurements. And Crystal McClure helped with some of the analysis at Davis and everybody else who contributed to the measurements overall. Thank you.